Now that we have our circuit entirely transformed into the phasor domain, we can apply circuit techniques that we've used before to find whatever quantity of interest that we want. In this particular example, we are interested in the voltage across the inductor component. And there's a couple ways that we could go about this. We could do some sort of loop analysis and find the current that's flowing through the circuit. And so one way to do that would be to say, all right, I'm going to find the current and multiply it by the impedance of the inductor. Or we could also look at the circuit and recognize that this is in fact a voltage divider. Even though we've removed the inductor and the resistor and replaced them with boxes, this is still a voltage divider. And so we can write out our expression as a voltage divider by saying that the voltage across the inductor is the impedance across the inductor plus divided by the sum of both impedances times the original source. And so if I plug in the values that we have from our preceding components, we found that the voltage source was 15 e to the negative j 120 degrees, that the impedance across the inductor is J4, the impedance across the resistor is 3, and that the impedance across the inductor again is J4. And then magically punch all these things into your calculator and then it works out. But one of the challenges we're going to have is that this is in a polar representation. This is in a rectilinear or Euclidean representation. And trying to do the math of multiplying a polar thing times a vector thing gets really annoying. Inside of your calculator, if you punch in either of these components, it will work out and resolve itself, but in the interest of doing these by hand, it's going to take some time. So for the sake of just this problem here, I'm going to do the math for you and tell you what the result is. I will later go back and discuss how we got these particular values, but for the sake of argument right now, let's just go with it and I'll tell you what the result of this calculation is. So if you were to perform this calculation in your calculator, the result that you would come out with would be in one of two forms. If it was in a polar form, it would be 12 e to the negative j 83.1 degrees, and again that is in volts. And if you happen to do it as a vector, the result of this calculation would be 1.435 and negative 11.913. Now, one of these formats is a lot more useful to us than the other. This allows us to directly transform back into a time domain representation, while this form in terms of the vector is completely correct, but it doesn't allow us to go back into a time domain expression. So for the sake of argument here, we're going to accept the polar form and move backwards into our time domain expression to find out what is actually the voltage across the inductor.